Hi everyone, welcome back. In this video, we're going to take a look at Chapter 7, Section 1, which has to do with trigonometric identities for precalculus, and we're going to talk about how we can prove identities using some basic identities. Okay, so to start off, we're looking at trigonometric identities, and we can say that two functions are identically equal if those functions, f of x and g of x, are equal for all x, where x is defined for those functions. So if these are equal for all x, then we would call them identically equal, or sometimes we shorten it and just say it's an identity. Identically equal. Okay, so this seems pretty trivial, like they're just equal to each other. But basically what we're saying here is that any x value we put into f will get the exact same value for g. In other words, they're identically equal, identically the same function. What we're going to be asked to do in this section is show that some identities are true. What that means is we're going to be given an identity, f of x equals g of x, and our task is to prove that this identity is true. So we can't assume this equation is true. We can't work with it like we would an equation that we assume is true. Instead, what we have to do is work with the equation, work with the functions actually individually, move them around, replace stuff. One of my college professors called it massaging the equation, so that we end up showing that one side is equal to the other side. So we're taking f of x, for example, and we're going to substitute values. We're going to simplify and work with it until eventually we'll show that we end up with g of x on the left side. And at that point, we've shown that f of x, when we work with it a little bit, not changing the values of f of x, just substituting, is equal to g of x. So at that point, we have proven that this original identity is true. So I like to think of these as kind of like the puzzles that we're given in this section. Our puzzles are we're trying to figure out what pieces we have to plug in order to show this equation is true. And in order to solve the puzzles, we're going to be using some tools from our toolbox. And the tools are just some basic identities that we can substitute into the equation so that we can work with and simplify the equation. So I'm going to scroll down a little bit here. Here is a list of our tools. Also, this is on page 447 of the textbook, Chapter 7, Section 1. This is going to be our toolbox. And then all of these are identities that we can use, we can replace into the puzzles that we're given in order to simplify or change one of the functions to look like the other function exactly. So these are important to know. Ideally, you would memorize them. And this is going to make it a lot easier to work on the homework problems. So for this section, definitely have this pulled up for the homework problems and be referencing and using this as you go through and prove the equations. Okay, so some of these are pretty straightforward. We should remember tangent equals sine over cosine. Cotangent is just the reciprocal of that. Reciprocal identities, we defined cosecant, secant, and cotangent using these. Pythagorean identities we saw using the Pythagorean theorem. We looked at the unit circle and we had a right triangle inside of there. And then the even odd properties we can see using the unit circle. You could also take a look at the actual graphs of these. So for example, graph of sine, we know it looks like this. Sorry. Yeah, exactly like that. And it's an odd function. So what that means is that if we, right here, sine of negative theta equals negative sine of theta. If we take sine of negative theta, it's going to be the opposite of sine of theta. So using those even odd properties. So we're not going to go through why these are all true. We've kind of seen these in the past couple of units. Instead, what we're going to do is use these to do a few practice problems. So I think the practice problems are going to be the most helpful in order for kind of like learning how to work and solve these puzzles. Okay, so let's take a look at our first example, example 1 from our textbook. You can actually find this in the textbook. Here we're trying to establish, which is just another word for prove, the identity that cosecant of theta times tangent of theta is equal to secant of theta. So what we're going to do here is we're going to choose one side and focus on manipulating or changing that side, substituting in values so that it looks like the other side. So let's take a look at this left side, cosecant of theta times tangent of theta, and let's use our ratios and our reciprocal identities to help us out. So cosecant of theta we know is equal to 1 over sine of theta, and tangent we know is sine over cosine. So 1 over sine of theta. So we're just looking at the left-hand side here. 1 over sine of theta times sine of theta over cosine of theta. Okay, so then now we can simplify. The signs cancel out. So we end up with 1 over cosine of theta, which we know we can rewrite as secant of theta. So now what we've done is by replacing or substituting in values, we've shown that this left side is equal to the right side. Secant of theta is equal to secant of theta. So we're finished. We've shown that the left side, when we substituted in values, we haven't actually changed the value on the left side, we've just substituted, is equal to the right side. So here's a really quick example of what solving these puzzles looks like. I want to go over what we should avoid doing. In other words, we don't want to assume that this equation is true and then work with it as a true equation. I'm going to clarify what that means right now. So we have cosecant of theta times tangent of theta equals secant of theta. And this is an example of what not to do. So we don't want to assume this equation is true and then work with it as we would a normal equation. An example here, cosecant of theta is 1 over sine of theta. Then we have tangent of theta, and then we have secant of theta. So here we could maybe realize, if we assume this is true, that secant of theta is 1 over cosine of theta. And then we might be tempted to do something like multiply both sides by sine. So multiply both sides by sine of theta. So these cancel out, and then we get tangent of theta equals sine of theta over cosine of theta, which we know is a true statement. Technically, this is correct, but because we treated the equation as true, we assumed it's true, we haven't actually proven that it's true. In other words, what we did here was we assumed what we were trying to prove. So we can't multiply both sides of the equation by sine if we don't know that this equation is true. So you should avoid thinking of it as a normal equation. Avoid multiplying both sides, avoid cross-multiplying. Instead, what we want to do is be isolating one of the sides and then working with the sides individually. And then at the very end, we can show that they're equal to each other. So we need to be really careful to not treat this as a true equation. This is the most common mistake that I see in this section. Okay, so that's our first example. Let's go over an example that's a little bit more involved. Let's take a look at example 3 from our textbook. So this one has sine squared theta, or sine squared negative theta. And remember, the squared just means we're actually squaring sine. It's kind of like on the outside, but we just put it in front of sine. Minus cosine squared of theta all over sine of negative theta. Sorry, and this should be negative theta up here. Minus cosine of negative theta. Equals cosine theta minus sine theta. Okay, so we're trying to establish or prove that this identity is true. So we can't treat this as an equation. Instead, what we're going to do is isolate one of the sides and then work with it from there. The left side is a little bit more complicated, it looks like, and also has some negative thetas. So I think we can do a little bit more work with it right away. So we're going to be looking at the left-hand side. The first thing we can do is we know that using our even odd properties, that sine of negative theta is equal to negative sine of theta. we also know that cosine of negative theta is equal to cosine of positive theta. So even and odd properties. So what we can do here is replace, instead of sine squared of negative theta, we actually have negative sine of theta squared. So I replace sine of negative theta with negative sine. And actually, I'm going to write out this step just to make it a little bit more clear. Here we have sine of negative theta squared. So it can be a little confusing with the 2 in front of the sine. Here we have cosine of negative theta squared in the same denominator. So what we're doing here is we're replacing the sine of negative theta and the cosine of negative theta using those even odd properties. So negative sine of theta squared, and then we have minus cosine of theta. Cosine of negative theta is equal to cosine of positive theta squared. All over that same denominator. Okay. Then we can simplify the numerator. Negative sine of theta squared gives us positive sine of theta squared. And then we have minus cosine of theta squared. All right, next up, we want to take a look and see if there's any other identities that could help us out. I'm looking at the denominator right now, actually. We can use our even odd properties to replace the sine negative theta and the cosine negative theta in the denominator as well. So here we have negative sine theta minus cosine of theta. Okay. Next, we want to look and see, are there any identities that kind of like pop out to us? And it can help to consider the right side of the equation. So if we look at the right side of the equation, notice that we have just one expression with no denominator. Yeah, so what we want to do here is try to rewrite these so that we can cancel out that denominator. We just end up with a numerator. If we look at the numerator, notice we have x squared minus y squared. So I just replace sine and cosine with x and y. And if we were to factor this, we can factor this into x plus y times x minus y. In the denominator, we have negative x minus y, which we can rewrite as negative x plus y. So I just factored out a negative 1. If we were to apply that to sine and cosine, on top we have sine theta plus cosine theta times sine theta minus cosine theta all over negative sine theta plus cosine theta. Okay, now notice by factoring, we can cancel out the sine plus cosine thetas. So we end up with, we still have that negative in front, negative sine theta minus cosine theta. And then looking back at our right side, we want to try and end up with cosine theta minus sine theta, which we can do just by distributing the negative. So at this point, we have manipulated our left side by substituting and simplifying all the way to the point where we ended up with cosine theta minus sine theta. So this is what we ended up with the left-hand side, and that is in fact equal to our right-hand side. And notice here, I didn't assume our equation is true. I didn't multiply anything on both sides. Instead, we looked at one side separately, and then we worked through that side. So we're finished with this example. It's not always obvious what to do in these, so you might need to try out a couple of different identities. You might want to check and see if you can factor at a couple of points. Here, the factoring was kind of like the key part, noticing that we want to get rid of that denominator. Okay, so let's take a look at example 6 from that same section. Here we have tangent of theta plus cotangent of theta all over secant of theta times cosecant of theta is equal to 1. So we're trying to show that this left side is equal to 1. Let's start off by switching these to sine and cosine. Maybe that'll help us maybe see some connections between the numerator and denominator. So tangent is sine theta over cosine theta. And cotangent is going to be the reciprocal of that. So cosine theta over sine theta. All over secant is 1 over cosine of theta, and cosecant is 1 over sine of theta. Okay, so we have fractions in both the numerator and denominator. What we're going to do next is see if we can combine this numerator to end up with just one fraction. In other words, if we want to add two fractions, we need to make sure their denominators are the same. I'm going to write this out on a separate section, sine of theta over cosine theta plus cosine theta over sine theta. So we want to end up with the same denominators. So we know we'll need a sine theta in the denominator. If we take cosine, multiply it by sine over sine, and we'll also have a cosine in the denominator. In other words, the common denominator we're looking for is cosine times sine. So in order to end up with that common denominator, we need to multiply by 1. So that is why we're multiplying by sine of theta both in the denominator and the numerator, to multiply by 1. Same thing on the right side, we're multiplying by cosine in the denominator, so we also need to multiply by cosine in the numerator. When we do that, what we end up with is sine of theta squared plus cosine of theta squared all over sine of theta times cosine of theta. And that is all over 1 over cosine of theta times sine theta. Okay, so I just multiplied the ones in the bottom. What we could do next is notice that this numerator up here is actually equal to 1. So if we have sine squared plus cosine squared, that's just equal to 1. I'm going to replace that 1 over sine theta times cosine theta. And then we're dividing by a fraction, so I'm going to multiply by the reciprocal of the bottom. So times cosine theta times sine theta. And that's all over 1. So finally, if we multiply these two, you notice that the numerator and denominator cancels out. So we end up with 1 over 1 or 1. At this point, we've shown that the left side of our equation is exactly the same as the right side. So 1, which is what we ended up with on the left-hand side, is equal to what we started off with on the right-hand side, 1. So we've proven or established this identity. So sometimes it is helpful, we can see from this example, to combine fractions if we have more than one fraction that we're adding or subtracting in the numerator or denominator. That way we can do some canceling out and simplifying. Okay, so the last example we're going to look at is example 7 in the textbook. Here we have 1 minus sine of theta divided by cosine of theta. And we're trying to prove the identity that 1 minus sine theta over cosine theta is equal to cosine of theta over 1 plus sine theta. We're trying to prove this identity. Here, you can choose to work with either side. I'm going to choose the left side. We have our left-hand side. We're looking at it separately. 1 minus sine theta over cosine theta. And I almost always rewrite it down here just to make it a little bit more clear what we're starting with. Okay, so the first thing we can do, it's important to consider what our goal is. So our goal, notice, is to end up with 1 plus sine theta in the denominator. So what we can do is actually multiply this by 1 plus sine theta. We want it in the denominator, so we're going to multiply the denominator by it. That means we'll also multiply the numerator by it. So we end up just multiplying by 1. So 1 plus sine theta over 1 plus sine theta. Because now what we end up with is 1 minus sine theta times 1 plus sine theta. And we're dividing by cosine theta times 1 plus sine theta. So now we actually have the other denominator in the right-hand side denominator. Now we have it in the left-hand side denominator also. Next, I'm going to expand the top. I'm not going to expand the bottom just because we want to try and leave this as it is. So let's distribute the top. We end up with 1 minus sine of theta squared, or sine squared theta, all over cosine theta times 1 plus sine theta. And now you might recognize at the top we have a Pythagorean identity. 1 minus sine squared theta is equal to cosine squared theta. Cosine of theta squared. And then what this allows us to do is cancel out one of the cosines. Cosine canceling out one of the cosines. So we end up with cosine of theta over 1 plus sine of theta. Now we've proven that the left-hand side is equal to the right-hand side. This is what we ended up with our left-hand side, and then the right-hand side, we just copy down from the beginning, 1 plus sine theta. And we're finished with that. For all of these exercises, when we went through the examples, we went through the correct way to do it. And you're not always going to know the correct way to do it. What I want to talk about is how to approach these problems and a few tips. So first, sometimes it's better to start with the more complicated side and try and get that side to be simplified a little bit. So containing the most complicated expression. A good step to take is to rewrite, if you have a sum or a difference of quotients or like fractions, for example, like plus or minus, try and rewrite that as just one fraction. So in this case, we would end up with a times d plus b times c all over bd. And that might help out with simplifying some of the fractions. Another tip, and these are from our book, sometimes only rewriting in terms of sine and cosine can be helpful if it's possible. Sometimes you'll have a lot of different trig functions, and rewriting it all in terms of sine and cosine or trying to simplify it or write it in terms of sine and cosine as much as possible can make it easier to see what might cancel out. Finally, the last one our book gives us is to keep the goal in mind. So always look at that other side of the equation and try and think about what we're trying to end up with, and that could help you out with identifying what steps to take. A few tips that I have is I think of these as puzzles. And again, we're using our tools, our basic identities, trig identities, as tools to solve these puzzles, which means that the answer isn't always simple and clear. Sometimes it's a little bit more complicated. So you might need to try several different tools before you find the right one that fits the puzzle. So for example, if the puzzle involves, let's say metaphorically, like screwing something in, and you try the hammer and it doesn't work, and then maybe you'll try the saw and it doesn't work, and then you try the screwdriver and that one works. So you'll be trying out several different identities sometimes, and then one of those will get you closer to proving the identity is true. If you're stuck, then one piece of advice is to look at similar problems. So try and look at the different example problems throughout the textbook, not only in this video, but the ones that are in the textbook. We skipped a few textbook ones, and see if there are problems that look similar to the problem you're working on, or look similar to the step that you're at in the problem you're looking at. And that can give you a clue as to what to do for that step in order to like progress in the puzzle. So definitely look at similar problems if you ever get stuck at certain points. If you're stuck, it might also be worth it to look back and see if there's a different tool you could use or a different identity you could use to help simplify. Okay, so that's it for trig identities. Our homework is going to be just practicing a bunch of these, making sure that we get used to looking at an identity and then substituting, simplifying to show that both sides are equal to each other. Again, making sure we don't assume the equation is true and work with it as we would a normal equation.